Okay, in this class I want to talk about Newton's laws again, continuing on where we built up from the last day. A few things again we'll just go over. We defined a force. A force is just a pull or a push on an object. We encountered tension, which is a pulling force from a rope or a string. We encountered resistive forces, which is a force whose direction is opposite to the velocity direction. And then we have tractive forces, which are just driving forces. We also spoke about choosing coordinate systems and understanding what we mean by positive and negative directions. Okay, they're important. We talked about Newton's laws. In the absence of a net force, a body at rest stays at rest, and a moving body continues moving in a straight line with constant velocity. That's important. So if something is at rest, it'll stay at rest. Okay, unless some force acts upon it, unless some kind of pushing or pulling force acts upon it. And a moving body continues moving in a straight line with constant velocity. So if something's moving and there's no net force, well, it will continue moving in a straight line with constant velocity. Okay, that's very important to space travel and things like that. There's not a huge amount of fuel needed to travel huge distances, because once you're heading in a straight line, you'll stay going in a straight line. Newton's second law, fundamental law of dynamics. This equation is really important. F net equals ma. And then the third of Newton's laws, if object A exerts a force on object B, then object B always exerts a force back on A. The two forces are equal in magnitude but opposite in direction to each other. Okay, so here we have a very dodgy, rough diagram, but what I have here is I've got a flat surface, and sitting on this flat surface is a Sherman tank, and this Sherman tank is attached here by a string which goes over a pulley, and hanging from the pulley is a paper clip. The Sherman tank has a mass of 34,000 kilograms, and the paper clip has a mass of 1.1 gram. Okay. What's important here is this. It says assuming all surfaces are smooth. So assuming all surfaces are smooth. What that means from our perspective is that there is no friction at work here whatsoever. So if all surfaces are smooth, then there is no friction force at work. So what happens? What's going to happen? Well, we can investigate this using force diagrams and see if this paper clip can make this Sherman tank move. Okay, this tiny mass, can it move this huge mass? Of course, we're talking about smooth surfaces, so we're removing friction from the problem. Okay, so what I'm going to do to examine this is I'm going to draw a couple of force diagrams. Okay, and I'll look at the force diagram for my Sherman tank first. Again, I don't have to draw a picture of the actual Sherman tank, but we're going to examine what is happening here. You know, the Sherman tank is pushing down on the ground, but the ground is pushing back on the Sherman tank. So the Sherman tank is pushing down on the ground, but the ground is pushing back on the Sherman tank. So what forces are acting on the Sherman tank? Well, the first force that's acting on the Sherman tank is the force due to gravity. And that force is called its weight. And we'll talk more about that particular force at a later date. But the weight of the Sherman tank is pushing down on the ground. Okay? Sorry, gravity is pushing down on the Sherman tank, I should say. So that force of gravity on the Sherman tank is called the weight of the tank. And that's pushing down. So gravity is pushing down or pulling down the Sherman tank towards the center of the Earth. Also acting on the Sherman tank, if that was the only vertical force acting, well, then the tank would accelerate downwards, but it's not going to. It's not going to go into the ground. It's just sitting there on the ground. So the ground is applying an upward force back on that Sherman tank. So gravity is pulling the Sherman tank downwards, and the ground is pushing back up on the Sherman tank with something called a normal reaction. Again, that's a force we're going to look at in more detail later on. What else is happening here? Well, there's a tension in this string. This is a string going along here. There's a tension in the string, and that's pulling to the right. I'm just going to call that T. What about friction? Well, there is no friction, and those are all the forces at work on the Sherman tank. Let me write ST over here for Sherman tank. The vertical forces here are cancelling each other out. This isn't sinking into the ground, it's just on the ground, ready to go. So our up forces and our down forces are going to be equal to each other. So I can kind of disregard those a little bit. And I'm going to think about the direction. I'm going to call this a right positive system, because the only force acting on it is pulling it to the right. So that's my force diagram for my Sherman tank. I'm also going to draw a force diagram for my paperclip. Again, all my objects in my pictures are just, I'm drawing them in as blocks. So what forces are acting on the paperclip? Well, there's the force of gravity pulling the paperclip downwards towards the center of the earth. That's the weight of the paperclip. And then there's a tension pulling back up against the paperclip, which is T. Okay. So those are my force diagrams. Let me just write PC over here for paperclip. So my force diagram for my Sherman tank looks like this over here, and this is my force diagram for my paperclip. The other thing I'm going to choose for my paperclip is I'm going to choose that to be a down positive system, because I think ultimately, you know, this is going to pull downwards. So what I'm going to look at now for each of these things are force equations. Before I do, I want to just talk about this force here, the weight of the paperclip. Okay, the weight of an object, well, F equals ma, force equals mass times acceleration. So the weight of an object is its mass times the acceleration due to gravity, mg. Okay, so the weight of this object is mg. Its mass is 1.1 grams. Now 1.1 grams, we need to change that into kilograms because we're dealing with newtons. Newtons are kilogram meters per second squared, so we need to think about its mass in terms of kilograms. So the mass of this thing is going to be equal to 1.1 divided by 1000. So what we're going to have is a mass of 0.00 times g. And maybe I might, just for ease, I might say g is equal to 10 here in this case. Let's take g to be about 10. So if g is equal to 10, that would be equal to 0.011 newtons. So the weight of the paperclip is 0.011 newtons. Notice the weight of the Sherman tank would be 34,000 times 10, which would be 340,000 newtons. Okay, but the vertical forces here are cancelling each other out, so we're not going to worry about that too much. So those are my force diagrams. Now I'm going to look at my force equations. And my force equation is from Newton's second law. It's F net equals ma. So looking at my Sherman tank, first of all, the net force. Again, the up and down forces cancel each other out, so I'm only looking at these forces to the right. So we're talking about horizontally here. so horizontally, for this force. Well, the only force here is T is positive, so my F net is T. F net, the net force pulling to the right, is T. And that's equal to the mass times the acceleration. Now the mass of this Sherman tank, I think we said, was 34,000 times whatever the acceleration is. So whatever the acceleration of that Sherman tank is going to be, my tension is going to be 34,000 times that acceleration. That's for the tank. Okay, there's my first equation. Okay, so that's my equation for the tank. Write in ST there. I'm going to look at the paperclip next. And the paperclip, you know, is only moving vertically here. So I'll write in vertically, but so we're dealing with the paperclip, the vertical forces on the paperclip. Again, I've said down is positive, so the net force is going to be a combination of this down, this positive 0.011 force, and this up force, which we've called T. So my net force is going to be 0.011 subtract T. And that's going to equal to M times A. The mass of this paperclip was 0.0011 times whatever the acceleration is. Because, and it's going to be the same acceleration as that of the tank. You know, if this is a string, if this pulls down, well then the tank will move across. And now I have a system of equations. I have two variables here, two unknowns I should say, tension and acceleration. So how do I solve them? Well, I'm going to solve for acceleration by just using a substitution. I'm going to take this value for T and I'm going to substitute it in there. So I can deduce, therefore, that 0.011 from equation 2, I'm taking this equation 1 and I'm plugging it into equation 2, and I'm saying therefore 0.011 subtract T, which is 34,000, A is equal to 0.0011 A. Okay, I'm going to try to solve for A. So I'm going to use my addition property of equations. I'm going to add 34,000 A to both sides. 0.011 is equal to 34,000 plus 0.0011 A. So we're going to get 34,000.0011 A. To solve for A, I'm going to divide on both sides by 34,000.0011. So I'm dividing here by 34,000.0011 and dividing over on this side by 34,000.0011. Okay, and they'll cancel, and so we have our value for A. It's going to be whatever that thing works out to be. So let me type this into a calculator. 0.011 divided by 34,000.0011 I'm not great with calculators. That's approximately, let me change that to an approximately equal sign. 3.235 times 10 to the power of -7 meters per second squared. So 3.235 times 10 to the power of -7 meters per second squared. So what does that mean, 10 to the power of -7? Well, that means if I took that decimal place and moved it 7 places to the left. So 3235. I'm going to take the decimal and from here and move it 1, 2, 3, 4, 5, 6, 7 units to there. So there's going to be my decimal, and it's 0.00000003235 meters per second squared. That's how fast this system will accelerate. But I guess what I'm trying to explain is that this system will accelerate, that the paperclip will pull the Sherman tank, even though it has a tiny mass, even though that has quite a large mass. The paperclip will pull the tank. Why? Well, because we've removed friction by making the surfaces smooth. Of course, in practice, a Sherman tank sitting on this kind of ground, there will be friction, and it'll be large, and the paperclip would not be able to overcome that friction. But if we could remove the friction, that paperclip can get that Sherman tank moving. Not at a particularly great rate, but it can get it moving nonetheless. Okay, so have a think about that. Keep practicing your exercises. Practice, practice, practice.